Okay, so this video is the proof for the neural tangent kernel. So the proof for neural tangent kernel. And just like the proof for the NNGP, it's a input-output proof. So the way these things are phrased, they're a proof by induction, but I'm going to package it into something that says if the input is like this and the output is like that, then the neural tangent kernel propagates from one layer to the next layer. And you can stack that together as your machinery bit for the proof by induction. So here is the proposition. Just like before, we have an fold and an fnew. And so this is called proposition 25 in the notes. So suppose you have some function fold, and in this one, the parameters matter. So in the neural NNGP thing, it was a statement about random functions and their distribution. But now this is a statement about gradients. So you got to make sure the parameters are in there. So the functions are a little more complicated than they were before because there's inputs as well as parameters. So here we go. N fold is going from R n in times the number of parameters to R n old. So it's a function we write like this, fold of x theta. Suppose this function obeys the following property. Obeys. If you do the theta derivative of it, with respect to the weights, so this thing is some kernel that is called capital theta of xx prime. By the way, one thing I guess I picked up in a elementary school was that capital thetas are a circle with an h in them. So that's how I draw my capital thetas. Okay, so it obeys this. If you do the gradient with respect to these parameters, which I'm calling the old parameters, then you get this kernel theta. Okay, the observant people will notice this doesn't actually make any sense because f old is supposed to be in R n old. So when you do these things, you don't get a function, you get a matrix. That's not what we want. So actually what we want is we want this, the ith component, to be this kernel function theta for every I. So this is for every 1 less or equal I less or equal the output dimension, and out, and old. Is it an old? And old, yeah. And the cross components, we want them to be 0. So theta fi old x theta 0 old transpose times the same thing with j. This is supposed to be 0 if I is not equal to j. Okay, there's an x prime missing here. Okay, so what this is saying is if our old function, when you compute this gradient thing, you get this old kernel theta old. Okay, then the conclusion is going to be that the new function that you get from the old function is going to obey theta new. So if the old function obeys it, then the new function defined as follows: f new. Okay, and here's the bit that's a little annoying, is the parameters for f new are slightly different than the parameters for f old. Why are the parameters slightly different? Because 2 new parameters got added. So here's the definition. F new of x theta new is defined to be sigma w over square root of n old w phi of f old x sigma old plus sigma b times b. And the point is that the new parameters are the old parameters union these weight matrix w and bias vector b. So the new function is the old function, but it has these new parameters in it that matter now because we're doing the gradients of the parameters, so that matters. Okay, so f new is defined like this, and the conclusion is that f new satisfies, or rather the gradients of f new satisfy that theta. So we're doing this new derivative, f new theta 0 new transpose theta it's converging to this new kernel, theta nu of x prime. And this is assuming theta 0 new is theta 0 old, and WB our chosen IID independent, mean 0, variance 1 Gaussians. Okay, so that's what it's saying, is the old function obeys this nice kernel rule, and the new function is going to obey this new kernel rule, as long as you define it this way. And the rule for the new kernel, okay, but there's one more thing, which is the same thing as before. Okay, this is a function whose dimension is Rn new, so this is f new from Rn times r to the number of parameters plus the number of parameters we added. Let's write that dimension of w plus dimension of b, and it outputs things in Rn new. Okay, so this is supposed to be a new by new matrix, so I'm going to look at the components. So this, for any I, it's going to converge to this, and for cross components, I not equal to j, it's going to converge to 0. That's going to converge to 0. So in other words, whatever the assumptions on the input f old were, the same assumptions are going to work for f new, and the only thing that's different is the kernel is something different. And how does the kernel propagate? The kernel propagates like this: theta new of x prime is equal to theta old of x prime times sigma prime of x prime plus sigma of x prime. And sigma prime. So sigma is exactly what appeared in the NNGP kernel. And sigma prime is the same thing with the phi function replaced by its derivative. So this is sigma w squared, expected value phi of z prime, plus sigma b squared, and sigma dot of x prime is sigma w squared, expected value. And then you do the derivatives of the nonlinearity. Okay, and I guess zz prime are taken, they're Gaussians with mean 0 and covariance structure given by sigma old. Okay, maybe I should label these sigma new and sigma dot new. I think that's what they're called in the actual theorem. Let's go see. Yeah, that's what they're called in the actual statement. So if you read the statement, that's what's going to happen. And we have this additional assumption, all the NNGP stuff. So the f old has to be a random function who is converging to sigma old, and f new will also, by the same result we had before, that will also, the f news, their distribution will be an NNGP with kernel sigma new. So that's an assumption as well. I think that's written down. Yeah, so we're assuming f old is also a GP, mean 0, and covariance sigma old. Okay, so basically this neural tangent kernel, the exact statement is like a superset of what we proved before. So it's what we had before, but with more stuff tacked on. And you have this theta thing, these parameters matter, and they evolve in this funny way. And you'll see where this comes from. This comes from a chain rule. So here's the proof, and it really is writing out chain rule very carefully and seeing what happens in the limit. And again, just like before, it's going to be a feature regression model with the features like what you'd expect involving these kernels, and they evolve like this because of chain rule. So let me show you how that works. So proof. So step 1 is to separate this, the thing we're trying to prove the convergence of, is the derivative with respect to these new parameters, and to separate out the derivative of the new parameters as the derivative with respect to the weights and biases plus the derivative of the old parameters. So here's the fact. So theta f new, this thing transpose times this. So this is the new parameters. Let me write it with a new so we make sure that we know. This is equal to the old parameters. So So I wrote it like this in the notes. This is the old parameters of the new function evaluated where it's evaluated. Plus the gradient with respect to the weights and biases. Okay, so this is the really key observation. So we're doing the derivative with respect to the new weights. And the new weights, remember, the new weights are the old weights plus the new weights and biases from this layer. So when you do the gradient with respect to the new weights, that's equal to the gradient with respect to the old weights with these new gradients with respect to W and B tacked on. So when you write out this inner product, you get exactly this. You have two terms. You have a term from the old derivatives, and you have a term from the new derivatives. The new derivative term, that's exactly going to be like the NNGP kernel, and it's exactly going to be the same argument as before. The derivative with respect to the new weights is exactly the going to the NNGP kernel. So that part is going to converge to this term. That's going to converge to this term, sigma of xx prime. So that's what this term is going to do. And then this term is the derivative with respect to the old weights of the new function. And the new function has this nonlinearity phi. So when you do this derivative, there's going to be a chain rule, and you're going to get the derivative of the old function times phi prime. And that's exactly what's going to turn into this thing. So you're going to have this times this. So that's going to come out of chain rule for these two things. So at this point in the argument, there's two separate arguments. One is talking about the yellow function converging to sigma. Okay, the sigma, these are sigma nu. So that argument is identical to the NNGP. The argument that this thing converges to sigma nu, that's identical to the NNGP argument. So I'm not going to repeat it. So you can go read the notes carefully. You can go watch the video before. That argument is precisely this. This derivative is exactly converging to sigma nu. And it follows by the Gaussian regression thing. And you can also check the correct on diagonal thing. So actually I should be doing this all with I's and J's. Okay, so I'm not going to do the yellow term because the yellow term is exactly the same as the proof before. But let's look at the green term. So you have to do the old derivative. And this is where chain rule comes in. So here's the fact. So the old derivative of the new function so this is the derivative Okay, so this is the formula. So here's the thing, right? In this thing, we're doing the derivative with respect to the old weights, and W is one of the new weights. So when you do the gradient with respect to the old weights, W is like a constant. You can pull that out. So these things don't count in this derivative. So we just pulled them out. They're like a constant. So what do we have left? We have the old derivative of the derivative with respect to the old weights of phi of the old function. And now we're very close to having something that we know before. By the way, there's no biases either because the derivative of the biases is 0. And now we just have to do chain rule. So when you expand this out with chain rule, you get this. Chain rule applied to this guy. So you get, what do you get? So, okay, you have to know how chain rule works for the function, which is entry-wise application of the nonlinearity phi. And this is a bit funny because entry-wise application of the nonlinearity phi is we've taken a function from R to R and we've lifted it to a function from Rn old to Rn old. So it's behaving in a funny way. And it turns out if you sit down and write it carefully, you should get the following, which looks a little weird when you first see it. It's the Jacobian of this thing is a diagonal matrix. So you get a diagonal matrix coming out of chain rule. And so I'm going to write it like this. Diagonal of phi prime of f old of x theta old. So that's the term coming from the derivative of phi through chain rule, and it's diagonal because of this funny thing about how we applied entry-wise. So the diagonal you should think of as coming from entry-wise application. Phi prime is the derivative of phi. So this is a big diagonal matrix. So this is a n old by n old matrix. The weights are n new by n old. And so that's the derivative of the outside function in chain rule. The derivative of the inside function is what we had before. So this is all multiplied by, multiplied by the old derivative of the old function, f old of x theta old. Okay, so this is a n old by n par matrix. Okay, so what have we done so far? We've just applied chain rule carefully, and you end up with this funny diagonal matrix. So this is the key formula, and it just comes from applying chain rule carefully. And now we're going to multiply it out, because what we need is we need to do this thing times its transpose. So there's a big multiplication you got to do, and that's what I'm going to do next. So again, maybe you want to read the notes where it's written a little more neatly than what I'm doing. So here it goes. So if you write it out, theta old of f new I x theta new transpose so if you write this out, what do you get? So you get a product, and each of these has a diagonal matrix in them. So when you multiply them together, you have two diagonal matrices you need to multiply. And there's these other funny things that appear. So what do you get? Sigma w squared over n old. So those are the prefactors coming out. So there's a factor of sigma w over square root of n old in each of them. You multiply them together, you get sigma w squared over n old. Then you have these diagonal matrices multiplying on either end. So you have a diagonal matrix of this nonlinearity, phi prime. Okay, so you have two of these diagonal matrices, one from each term. And there's no transposes because the transpose of a diagonal matrix is the same matrix. Okay, so those are the diagonal matrices. And then you have, in the middle, you have the gradient with respect to theta old multiplied by itself. You have the gradient of theta old multiplied by itself. So that's what goes here. But we were told in the hypothesis of the problem that the gradient of theta old multiplied by itself is exactly what the kernel theta old is. So by the hypothesis, that's exactly what theta old is. So in the middle, this multiplication is supposed to be a big matrix multiplication of the old gradients. But we know what those are. They're exactly theta old. Okay, so here's the other little hiccup. Again, right, we said theta old is supposed to be a scalar function, and we're looking at components. So it's actually supposed to be a matrix here, and it's the matrix that has theta old on its diagonal. So this ends up being another diagonal matrix, and that diagonal matrix was hidden inside the fact that we had this thing for I, and we had 0 for I not equal j. So actually we have two components. We have theta old and zeros, and that's why over here what I'm going to write down is a diagonal matrix. In the original papers where this was written, this appears as a tensor product. So I want to avoid using tensor products. That's why I've done it this way. So I think you have to do a little pain either way you go. But this is the painful way with no tensor products. Okay, so what do you end up with is this diagonal matrix. Diagonal matrix of theta old x prime. And that comes from the hypothesis. So I'm going to highlight this in green because it comes from this green hypothesis way up here. So by this hypothesis, that is what we are replacing at this point, because when you multiply these two things out, you have the gradient of the old parameters, and we know those are theta old. Okay, so now you have a product of three diagonal matrices. What am I missing? I forgot to put the weights. Let me put the weights back in. So there's also these w's that appear on either end. So you have w sigma w squared over n old. You have the weight matrices w, and on the end, you should tag on another weight matrix w. And we're doing the ij component, so we're doing the ij component. So what you end up with is the ith and jth columns of w. So it should be wi, I wrote it like this in the notes, wi dot over here, and over here it's wj dot transpose. So the ith row of w gives you fi new, and the jth row of w gives you fj new. And so that's why we've got this big crazy thing going on. And the dot means, you take the ith row, you treat it as a vector, and you multiply it all. Okay, so this is the expression, and this is the expression that we hope will converge to the thing we want. And the way you can see it converges to the thing we want is to write it, instead of writing it as matrix multiplication, is to write it as a big sum. And then you'll see what happens. So let's write it as a big sum. Sigma squared w over n old. So yeah, this is a 1 by n old vector. So when you're multiplying it out, you're doing a big sum over n old things. So that's what we're going to write here. So we're going to use the letter k. K equals 1 to n old, and we're doing the sum over wik over here. And we have a bunch of diagonal matrices. So when you multiply by diagonal matrices, you're picking out the kth element of each of them. And the kth element of each of them, well, in this middle matrix, all the elements are the same. In this one, you get the kth component. So you get to phi prime of f old of x theta old k. So the kth component of that vector. Then you have theta, this is supposed to be capital theta old of x prime, phi prime of f old x prime theta old with a k, so the kth component of that, and then you multiply by the weight matrix over here of size from the jth row. So this is wik, and then you have wjk. Okay. All right, so here we go. So here's the point. Here's where things get nice. So 1, if I is not equal to j, then these are independent Gaussians. And we're adding up n of them. They're mean 0 because they're independent. And so the whole thing is going to converge to 0. So if I is not equal to j, this whole thing goes to 0 since wik and wjk are independent. So we're adding up a bunch of mean 0 things. The whole thing is going to be going to 0 if I is not equal to j, because these things are independent. So it doesn't matter what these things are doing, but in any case, these things are independent, it's going to 0. If I equals j, then this is a sum of a Gaussian squared, and that's not mean 0 anymore. So now we have some finite mean, and we're doing the average because we're doing the sum from 1 to n old, and we're dividing by n old. So we're going to converge to the expected value of this thing. And the expected value of these terms is 1, and these terms are all also identically distributed. So that was the hypothesis on the f old function. So what's going to happen in the limit, we're going to converge to the expected value of everything. These terms give a 1. So we're going to end up with is sigma w squared times the expected value of all of this stuff. And you might notice the theta hat old is just a constant. That pops out. So what you end up with is this, phi prime of f old x theta old 1. So any component, you can pick your favorite. Phi prime of f old x prime theta old 1. And you multiply the whole thing by this constant, which is coming out. So theta hat old of x prime. Okay, and that is precisely the definition of the kernel sigma prime. So this is theta hat old of x prime times what we call sigma dot nu of x prime. Okay, so I think at least when I do this calculation, it gets a little hairy at the end here, and I have to sit down and think hard of why these things are coming out with these diagonal matrices and why it's coming out like this. And I couldn't avoid turning it into a sum at the last second, but that is the way the proof goes. And hopefully you can see where these terms are coming from. So theta old is coming from the gradient of the old layer, and by chain rule, this is the sigma prime is coming out in this way with the phi primes. So if you understood the things about the feature regression, then the random feature regression, I think this one is very slightly more difficult, but not much more difficult. So hopefully that warmed you up well enough. You got something out of this. I know it got a little messy at the end. Definitely check out the notes for some clearer writing. Okay,